All right, so today we're diving into a really fascinating paper called Jstprove, and it tackles one of the biggest questions in tech right now. How can you actually prove that an AI is telling the truth? I mean, think about it. As these AI systems make more and more critical decisions for us, we've got to have a way to check their work without being able to look inside their brain. And this right here is the absolute core of the issue. We're not talking about whether you can trust an AI with your music playlist. We're talking about really high-stakes stuff. You know, when an AI is involved in a medical diagnosis or a multi-million-dollar financial trade, just trust me is not going to cut it. We need actual mathematical proof. And you know, this isn't some far-off sci-fi future we're talking about. This is happening right now. As the source material points out, AI is already at the very heart of these critical fields. It's helping spot cancer, it's predicting how markets are going to move, it's stopping cyber attacks in their tracks. These systems are making big calls with massive real-world consequences, which means our ability to trust what they're telling us is just as important as how accurate they are. So that real-world impact, it leads us straight to this huge problem. The very models that are so unbelievably powerful are often completely opaque. We can feed them data, and they give us an answer, sure, but that complex journey that happens in between, it's a total mystery to us. It's what we call a black box. This creates this fundamental conflict for pretty much everyone involved. I mean, if you're a client paying for an AI service, you need to know that the model is actually doing what you paid for. But the company that built it can't just hand over their multi-million-dollar model for you to inspect. That's their secret sauce. So you're stuck in this impossible situation. How do you prove something works without giving away the recipe? Okay, so how do we solve this puzzle? Well, this is where things get really cool. The solution comes from a field that honestly sounds like it's straight out of science fiction. Zero-knowledge machine learning, or zkML for short. It's a way to get the proof that we need while letting everyone keep their secrets safe. Now, the engine that drives all of this is something called a zero-knowledge proof, or a ZKP. Here's a really simple way to think about it. I can prove to you that I know a secret password without ever actually telling you what the password is. In the world of AI, the prover, which is the AI, convinces a verifier that it did its job correctly, all while revealing absolutely nothing else. No data, no model, nothing. And what makes CKPs so powerful, so unbreakable really, are these three core ideas. First, completeness. If you're an honest prover, you can always succeed. Second, soundness. A cheater can't fool the system. And third, and this is the most important one, zero knowledge. The verifier learns absolutely nothing confidential. It's a mathematically perfect little system for creating trust where it didn't exist before. And that right there is the magic trick. By using ZKPs, an AI can look at your sensitive medical data using its top secret algorithm, and then just spit out a mathematical proof that says, hey, I followed all the rules, and this is the result I got. You get the verification you need, and both your private data and the AI's model stay completely secret. So this sounds amazing, right? Like the perfect solution. Verifiable, private AI for everybody. Well, not so fast. There's been this massive hurdle that's basically kept this incredible technology locked away, accessible only to a handful of elite cryptographers. Here's the problem in a nutshell. You've got two completely different worlds. The engineers who build AI models, they live in a world of TensorFlow, PyTorch, and data science. But the experts building these zero-knowledge proofs, they're dealing with things like elliptic curve math and finite field arithmetic. It's just mind-bending stuff. And these two skill sets almost never exist in the same person. Your average machine learning engineer can't just decide to whip up a ZKP for their new model. And the paper itself just lays it out there, plain and simple. Bridging these two totally separate worlds is the central challenge. To make this kind of verifiable AI a widespread reality, you don't just need the theory. You need a tool that can speak both languages fluently. And that's where Jstprove comes into the picture. It was designed from the ground up to be that bridge, to be the translator that finally puts this incredibly powerful technology into the hands of the entire machine learning community. So how does it pull it off? Well, in essence, Jstprove takes all that ridiculously complex math, the elliptic curves, the finite fields, all of it, and just hides it completely. It packages the entire cryptographic pipeline into a simple, easy-to-use toolkit that any AI developer can use. No PhD in cryptography required. And this is what that simplified workflow actually looks like. It's incredibly elegant. A developer just runs 4 simple commands. Compile turns their AI model into something called a verifiable circuit. Think of it like a mathematical blueprint.
Then Witness runs the data through that blueprint. Prove generates the actual zero-knowledge proof. And finally, Verify checks it. That's it. All that insane complexity is just gone.
Now, having a simple workflow is great in theory, but making it actually work and work efficiently in the real world, that's a whole other ballgame. So the researchers behind Jstprove didn't just stop at the theory. They benchmarked it to see if it's actually practical for the kinds of AI models we use today. And they didn't mess around. They tested it on some serious hardware, a modern Apple M3 Max chip. So this wasn't just a toy problem. This was about seeing if the system could hold up under a realistic, pretty demanding workload. So let's look at the results for that compile step, which is usually the most intense part of the whole process. A model with over 200,000 parameters takes about a minute. A large one, with almost 2 million parameters, compiles in under 45 minutes. Now, you have to understand, for years, creating ZKPs for something this complex was seen as computationally impossible for any practical use. The fact that these times are not just possible, but completely manageable and predictable, is a huge breakthrough. And that is really the key takeaway from all their performance tests. Yes, bigger models take more time and resources, but the relationship is stable, it's predictable, and that's what elevates verifiable AI from a fascinating academic idea into a practical engineering reality that developers can start building with, like right now. So let's just zoom out and look at the big picture here. Jstprove makes this stuff accessible to the people who actually need it. Its code is open source, which makes the system itself transparent, and all of that creates a clear path to real accountability. It helps build what the paper calls a trustless future. Now, that doesn't mean a future where we're all paranoid. It means a future where we don't have to blindly trust. We have proof instead of faith. Imagine verifying that your credit score was calculated correctly without the bank ever having to show you its secret formula. That's the power of this shift. And that leaves us with this one final, really powerful thought. Just imagine a world where every single critical diagnosis, every financial trade, every security alert made by an AI could be independently and mathematically proven to be correct. That is the future that tools like Jstprove are starting to make possible.